and then we're off to the talk. Dr. Yortsos is the Dean of the USC Viterbi School of Engineering and also serves as the Zokreb Kaprillian Chair in Engineering, a position that he's had since 2005. He received his degrees in chemical engineering, the PhD from the California Institute of Technology. He's a member of the National Academy of Engineering and has served on the member of the NAE Council for several years now. You know, it's really great to actually have an opportunity to listen and give a talk on this work. The second speaker is Assad Oberai, who's the Hughes Professor of Aerospace and Mechanical Engineering, and he's also serving as the Interim Vice Dean of Research at USC in the Viterbi School of Engineering. Prior to joining USC, he was a professor in the Department of Mechanical, Aerospace, and Nuclear Engineering at Rensselaer Polytechnic Institute, where he was the Associate Dean for Research and Graduate Studies in the School of Engineering and the Associate Director of the Scientific Computational Research Center. So anyway, welcome to both of them. So they're going to give a joint talk today, and the title of their talk is a Spatial Temporal SAR Model for Modeling the Spread of an Infectious Disease, which is obviously very relevant to today. So I'm going to turn it over to Professor Dean Yortsos first.
Well, thank you, Craig. I appreciate the introduction. It's a pleasure to be here. This is work that was motivated by trying to understand the spread of the disease. I have not been in the area of epidemiology for sure, so that's not something that's not an area of expertise. However, the more I was looking and considering how people model this effort, it reminded me a lot of chemical reaction processes because in many ways the key phenomena are there. You have populations of, in this case, of people that are, you can think of them as different species. These are people that are susceptible, those that are infected, and of course those that are recovered, which is the standard assumption that is made in the model of most of the epidemiological models. But infection can be considered in many ways as a chemical reaction because essentially you have change of properties as after the a particular interaction or a collision or a frequency of contact that is happening. And in many ways, this is a problem that it is very well understood in the area of chemical reaction engineering. At the same time, you have phenomena such as advection. These, for instance, are issues related to transport as you go from one place to another. There's also phenomena related to diffusion or dispersion as people mill around or move around, and therefore you have different ways by which you can perhaps simulate things that are very similar to, although different in a different way, to molecular diffusion as well. I'll share my screen and then I will go through the presentation. And so let me go down to my, I don't want this to be the case. So this is work that in fact I put together, I started working on it in my spare time as a dean, maybe a weekend here and there. Most of the work, believe it or not, happened during the Memorial Day weekend, where we had some extra day. And I was able to sort of put together some sort of a dedicated time to try to understand that. And I shared it with Assad, the original ideas. Assad then had some very interesting feedback to the model that I had. And we worked together to improve it and also create some interesting simulations. This is a work in progress. It's not to a point of being in a position to be published as we speak. However, many of the ideas, I think, some of the ideas, I think, are original. What we want to show you today is perhaps an approach to the spread of epidemics from more classical, let's say, chemical and mechanical engineering approach to this. I know that we had an event yesterday, a joint symposium with IISc, Indian Institute of Sciences in Bangalore, and I appreciated very much an agent model that was created there, which was very nice and very interesting, which in essence is a different way of expressing what we do here, except that it is done in an atomistic way and with individual people, individual entities as well. But do consider this as an attempt to sort of put some perhaps better understanding of kinetics as well as of transport and reaction. So I will use differential equations, which is something that can soothe the brain and the mind when you're an administrator. You can use some differential equations, and the life is beautiful. It doesn't have to deal with budgets or things like that. So in conservation equations for the three species, which we will consider here, that's susceptible, infected, and recovered. In the original model, which we will also consider here, it's called the SIR model. The recovered fraction also includes those who have perished. And you say the question, you can ask the question, of course, that's not a good idea. The truth is that perhaps because the perished, the composition, the fraction of those who have perished as a result, as a fraction of those who have recovered is very, very small. So I don't think you made any significant mistake by doing that. How do you go about modeling a conservation equation for this species? The original model was published, 100 years ago. S, I, and R reflect, or they represent numbers, the number of people. But in fact, that is not a good variable. And so the first thing to understand is that actually we have to talk about densities. So you have to consider number per unit volume. For example, in a concentration in a solution, this is how we work. Or in the case of infections, number per unit area, because typically you're dealing with areas where people congregate and so on and so forth. So from now on, we are going to consider the species to be represented by their concentration, which is number per unit area. This is a very important distinction because the main mechanism of infection is proximity most of the times. And therefore, what matters is how many people or the density of people per unit area. So per unit area is a key item that we have to consider. So the first equation, well, actually there are three equations for the susceptible, infected, and recovered people. Has the standard form of a accumulation term, a convective term. This is advection. Let's say you take the train, many people take the train or airplanes or whatever to go from one place to another. There is a mechanism for diffusion or dispersion, which is something that we have been grappling with, whether it's how to represent this dispersion, because dispersion of molecules through Brownian motion is not the same as dispersion of people, which obey very different dynamics. It's kind of a fascinating way how you would represent this for people, but that's something that is a different question. And then on the right-hand side, you have reaction rate. The reaction rate is either rate of generation, in other words, you have more infected people, or rate of decrease, in which the number of susceptible people decreases as well. So the three entities together add up to the total number of people per unit area. I will also use the Greek letter rho to indicate density later on. And so if you add these equations, you have another equation for the anti-density of the population. This is the rate of change of the density because of advection and because of diffusion. The overall rate of change of populations doesn't change as a result of reactions because all three of them add up to one or to a constant. And so in this sense, you have these to close the equations of the conservation equations. This is a typical equation in fluid mechanics called the continuity equation. Most important question is, what do you do with the kinetics, the mass action kinetics? And so the reaction rate is we follow a standard approach from chemical reaction, that's a theory, which says that if two molecules, let's say S and I, collide, then the rate of reaction depends on their concentration, so the product of this, which is indeed the case, multiplied by a constant, which is essentially characterizing the frequency of the reactions, the rate of contact plus other things as well. And there is, in the case of infections, you have recovery, the recovery is depends on the it's almost like it's a first order reaction. It's almost like a reaction that you have a decay, radioactive decay, if you wish. This is the concentration, this is the rate equation for the susceptible, and this should be a product of the two concentrations of susceptible and infected, again with the same reaction constant. And then this is for the case of recovered, which is going to be proportional to similar to the SIR model, to the infected concentrations. I like to point out a few things here, because these are important to the understanding of what we do here. The first thing is to notice that lambda is an inverse time. This is the dimensions this is essentially the intrinsic rate at which an infected individual either recovers or dies. I believe this number is of the order of about, 14 days or maybe more. And that's a characteristic of that particular reaction. Again, we should make a point here that this is not a fine-grained model. Truly fine-grained models can allow demographics, health conditions, in other words, to take the various populations and further subdivide it in many different things. And I think a good process model should do that. And I'm sure many process models are doing this as well. Here, we try to create some generic way to look at the problem. Certainly, if one wanted to do something much more complex and much more elaborate, one could do that. Kappa is it has dimensions of inverse time and inverse concentration. So why there is a time coming in here? In the first case, in the lambda parameter, time has to do with the way by which your organism reacts, right? So it's a matter of, if you're infected, how long it takes for your immunity to fight the disease, and there's a characteristic time at which you recover. K here, or kappa, has dimensions of time, because this is a rate of reaction on how a susceptible individual becomes infected. Clearly, that will depend on the frequency of the contact and also the contact rate, the collisions. This is not very different than the case of, let's say, ideal gases that interact. You have a gas interacting with another gas to form a third chemical, create a chemical bond. And there are many theories in statistical mechanics that people use in order to estimate these contact rates, the collisions and frequencies. People use concepts such as the mean free path, which is an indicator of how often, what's the distance between two molecules before they collide on average. You can use all kinds of sophisticated modeling. You can use the Maxwell equations for the distribution of the velocities and many, many interesting things. However, in the real case with infections, that is not necessarily the mechanics of the kinetic theory of gases, because people interact differently. Encounters are not elastic. In other words, and the frequency of contact is different. Contact lasts for a substantial amount of time, and so on and so forth. So you would expect that this parameter would depend also on density. You can see it has the dimensions of time and also density here. And indeed is the case. Spatial distancing tells us that, let's say, above a certain number of feet, at 6 feet, let's say, or below a certain density, because this will correspond to 6 feet, the infection rate should be 0. So this parameter kappa has to be 0 if the density is less than a certain minimal density. This is actually interesting to me because I have never seen it in any of the publications that this parameter K or kappa is a parameter that depends on density. And we expect also that it's an increasing function of density, and the density increases from this parameter to a maximum parameter distance. Let's say that's maximum packing. Maximum packing will be, let's say, in a soccer stadium where people are packed next to each other, or let's say in a concert, or in any particular applications where people are packed together. Maybe in an auditorium, in schools and so on and so forth. And so you would expect that this parameter therefore depends on density in this different way. The moment you introduce dependence on density, then immediately the questions of how density is distributed in space becomes very important. That's why a spatial model is very necessary in order to accurately capture the kinetics of infection for, including in this particular case, COVID. And also what you can see here, it is meaningless to provide area-wide averages, let's say for states or countries, if there is a significant differentiation of density within these particular areas. Let's say when you talk about New York State, it's meaningless to talk about the state itself. It is much more meaningful to talk about the city, an urban area or a suburban area or rural areas, because they will have hugely different densities. As a result, they will have different performances in terms of this. So our model allows this to come in a natural way, assuming, of course, that we know how to capture the density variations in space. I went too fast here. Also, let me say that the formulation assumes that an infected individual infects a susceptible one at the same rate. It's not clear that's the case. Obviously, in practice, we remove infected individuals from circulation, but let's assume that they are all asymptomatic so that we don't know whether they are infected or not. Also, we made an attempt to evaluate diffusion coefficient. Let's say if you go to work in an office and you spend the day there doing random walks around your office, we estimated that the diffusion coefficient is about 10 to the minus 3 meters squared per second, which is, assuming that you do maybe on average about 6 meters or so, I think it's 6 meters of distance around the place where you work. It's about 2 orders of magnitude larger than molecular diffusion of gases. So clearly, dispersion of people and diffusion of people is faster than molecular diffusion of gas. Again, that is not necessarily. I think that's an interesting topic. How do people diffuse or disperse subject to certain conditions? So you can make this in a dimensional notation. Here, we just write the full equations in their glory. We create what's known as a Pecklin number, which is a very common term in fluid mechanics, and expresses transport versus, well, that actually should be diffusion. So it's an equivalent Pecklin number. We have a diffusion term called C, and we have the classical parameter R0, which in our case, we define explicitly as kappa times the density divided by the characteristic, inverse characteristic time lambda. And these equations can be hyperbolic or parabolic depending on the model taken and depend on spatial density and can be solved. So Assad and Harry were able to help simulate a lot of that. Right now, as I mentioned, we're doing only a few of this. So we have simulated some simple cases. One, the standard SIR model. Let me say that the standard SIR model, which is a batch reactor model, meaning that think of this thing as everyone being in a one volume, well mixed, and then you start from time t equal to 0. There's some infection, and then you can see how the infection spreads, but only in time, not in space. I should mention that if you have any variations in the initial conditions, then you have fluctuations. And because you are averaging in the chemical reaction, you are averaging a product, then this also will involve the product of the fluctuations as well. In the traditional SIR model, the only terms that are taken are these ones here. In other words, people make the assumption that the average of the product is the product of the averages, which is a no-no in, let's say, turbulence, where when you take, let's say, the average of velocity square, you also have fluctuation square. In fact, that's the intensity of turbulence. We believe this term can be important if you have fluctuations in space, and then our model would be able to figure out how much you miss by making this assumption and how much you miss as a result of that. This is a work in progress, and we'll try to figure out soon enough. Then you can do things like enforce health policies after an elapsed period of time. Then an interesting question is, can you import infection, and how important is that? I mean, people have said, the question, the political question, the policy question has been there to, restrict flights into a country. The question is how important it is and what's the effect of that. So one could actually measure it and use our model, because our model allows fluxes in and out from an elementary volume. The more important question is the variable interactions in space and the effect of diffusion. So now I'll stop and I'll ask Assad to take over and describe some of the simulations that he and Harry have done.
Okay, thank you, Yannis. So let's see, I'm going to now start sharing my screen, and hopefully I'll start exactly where Yannis left off. And here we go. Okay, so so when Yannis sent this set of notes, I was immediately intrigued, and being a computational person, my first impulse was, well, how do we simulate this thing? And so I recruited Hari, who's a PhD student working with me, and he coded up these equations in a finite element code, and we started solving it. And I'm going to run you through a few of the simulations that we did. The first few simulations are all homogeneous. So we're going to assume that we have the same density in the entire domain. And so we'll be looking at pointwise quantities, but basically it's the same value in the entire domain. And the last simulation is where the effect of space will come up, right? So let's start. So this is standard SIR curve that many of you have probably already seen. This corresponds to a value of R0, which is some sort of a non-dimensional reaction rate of 5. And many people say for COVID, the R0, when it is completely unchecked with no policies, is around 3 or 4, right? So this is something that is more virulent than COVID-19. And so, what's plotted here is the blue curve here that you can see. That's the fraction of people that are infected at any given time. The red curve is the susceptible population. So you start off with an initial condition where 10% are infected and 90% are susceptible. And the green curve that you see here are the people who've recovered or passed away, right, in the SIR model. And so the horizontal axis is time, and it's non-dimensionalized by 14 days, right, which is the rate at which the disease is over. So you either recover or pass away. And so what you see is unchecked. This is a really virulent case, and quickly the number of infected people increases from 10 all the way to about 50% in about 14 days, right? And then sort of starts to decay. And corresponding to that, the number of susceptible people drops precipitously, right? And the disease really only ends when almost everyone is infected, right? So the number of susceptible people is down to 0, and the number of recovered people is almost up to 100%. And that's where the disease ends, right? So without any checks. And so this is a virulent disease. This is what you would expect. So now Yannis was mentioning policies, right? So let's say after about a week, people realize things are going really bad, and at this non-dimensional time, t equals to 0.5, they institute a policy where they say there is strict social distancing, and you got to obey that and all that. And what you're able to do is you're able to bring down the R0 from 5 to 0.5. So this is a drastic drop that somehow you're able to get, right? So this is like, a strict social distancing, physical distancing, and all that comes from it. So what's going to happen when you do that? What's going to happen is immediately the infection rate is going to drop, right after that. And what will happen to the susceptible population is more and more will get infected, right? But at a much slower rate. And then if you wait long enough, now the disease is such that not everyone has to be infected, right? So by the time the disease ends, there is about 45% who are susceptible, who are still in the population, and about 55% who have sort of gone through the disease. And that's the equilibrium that's achieved in this case, right? So you've sort of, this would be the herd immunity for this particular value of R0, right? And so that's what this is, right? So that's great. Can we do something else? So yes, we can, right? So let's say after about 7 times 14, whatever that is, days, you say that we've had enough of physical distancing, we're going to lift that policy. What would you expect, right? So at 7 days, you had social distancing in place, the infections dropped down. But at this point, infections are really low. The infection rate is really low. It's less than, it's around maybe 1 or 2%. You say, okay, we're going to now remove those policies, right? What's going to happen? Well, what's going to happen is you will again see a rise in the infection rates. and you will again see a drop in the susceptible population, and then later there'll be a lag and you'll see an increase in the recovered population. And the steady state that you'll reach is not that different from the steady state you would have achieved if you sort of not instituted any policy, which is basically that that most people would have gone through the infection, right? So about 95% of the 92, 93% of the population would have got infected. So in some sense, you could argue this to a less dramatic measure is what we are going through right now, right? This is the stage where these policies have been removed and we are seeing a slight growth in the number of infections all across the country, I think. Okay, so these are all cases where everything was homogeneous. The one that I want to end with now is a case where things are varying spatially. And I want to in particular highlight the effect of diffusion. Okay, so let me play this here. What this is basically imagine like a spatial domain. So maybe think of this as a grid of about 50 by 50 kilometers. And we have an infection hotspot here. So what I'm plotting here is the density of infected people, right? And you can see it's a hotspot here, about 20% peak here, and then it's a Gaussian, it dies down. And what I'm plotting here is going to be the variation of the density of infected people as a function of time. And this is a Gaussian. And so what's really happening here, and there is no diffusion at all right? So I'll play this again. And what's really happening here is, more and more people are getting infected, right? Because of the SIR term, because of the reaction term. And you can see that is spreading out, right? Because, out here, there are very few people who were infected to begin with, but if you wait long enough, the infection rates rise, and this front reaches that, right? And the interesting thing is you see in the middle here, it becomes blue again. And the reason it becomes blue again is people who are already infected are now recovered, right? So they fall into a different category. But basically the infection has swept through this entire region, right? But here there is no diffusion. And what will happen is if you sort of wait long enough, this front will stall. It will not spread everywhere because out here, there is no infection and the infection will never get there, right? So clearly that's not physical. That's not what you would expect in real life. In real life, if you add a little bit of diffusion, this is what happens. In the same time scale, the infection spreads like crazy, almost like wildfire. And in the same time scale, this whole region is sort of passed through that infection, right? And everyone sort of has gone through the infection and sort of fallen into the recovered category. So it's interesting to play both of these at the same time, and then you can realize what the effect of even a small amount of diffusion at this front is, right? Because it basically pushes the population just ahead of the front to be infectious enough so that the sort of the reaction term in the SIR equations boosts it up, and you get a dramatic increase in infection. So I think that's pretty much all that we had to say. I think there might be some time for questions.
Great. Okay. Thank you both for the talk. So if people have questions, they can post them on the Q&A. Just go to the Q&A tab at the bottom of the screen. You can type in your questions and I will read them.
Yeah, there was a question about whether we can provide stochastic approaches to this. And the answer is yes, you could. Right now, our motivation was to try to understand a little bit more the mechanics of this before you go into a stochastic approach. You also have, machine learning AI approaches, which are essentially model independent, and they use essentially you learn the machine learning model learns from the behavior. This is more of a different approach. It's kind of a more classical approach. Whether it has validity, usefulness or not, I believe that you learn a lot of the things that you don't learn otherwise. But certainly it's one way to be able to educate yourself about what's happening. Whether it can be used for policy, development of policy, that's an interesting question. I think if we were to explore a lot more the spatial effects and diffusion effects, I think we will understand a little better what the impact of this is. And this is because it's a nonlinear system, because you have nonlinear kinetics. I think that can provide some interesting novel things that we do not anticipate for a linear problem.
Okay, great. Thanks. One more question, and then we'll go to the other talk, which is, did you do any simulations where R naught had different values to see what curves most closely match the data for the current virus?
So maybe I'll take that. No, we haven't done that yet, but that is actually quite a standard thing that is done, right? So when people have these SIR models, they look at the trends of what's going on in a given region, and then they change the value of R naught to best match what has happened up until that point. You could call it model calibration. And then they have a model, and then with that model, they can predict what's going to happen in the future, given the policies don't change. And of course, there is a bound of certainty that goes with that. But we haven't done that. I think what will be interesting is to do that, but probably more interesting to do, is look at the spatiotemporal effects, right? To actually see how the disease is spread historically, both in space and in time, and see if we can capture that with our model.
There was a question about Levy flights, which I like to take. Hyperdiffusion or processes of this type are common actually in the subsurface. I happen to have done a lot of work in that area for transport and reaction in porous media and the like. And such techniques actually are used quite a bit and could be actually very useful. And the answer, we have not done it, obviously, as you can see. But definitely you can do a lot of interesting correlated flights, if you wish, that are not random walks. And I think that would be a very good thing to do as well. Yeah, so now you're tempting me to go more into science and less into administration. I don't know how I can do that. One of these days, maybe I will.
More fun these days, yes. Anyway, thank you both for the fascinating talk. I'm going to turn it over to Bhaskar now to introduce our next speaker.
Great. Thank you, Yannis and Assad. That was a fantastic talk. Really appreciate understanding it better. So I'd like to introduce our next speaker. Professor Urbashi Mitra is the Gordon Marshall Professor in Engineering at USC. She received her PhD from Princeton University. She's a fellow of the IEEE, a founding editor-in-chief of the IEEE Transaction on Molecular, Biological, and Multiscale Communications. She's an expert in wireless communication networks and statistical signal processing. She has been the recipient of a number of awards, including the NSF Career Award, the 2017 IEEE Women in Communications Engineering Technical Achievement Award, and a number of others. Without much further ado, I'd like to turn over the floor to her for her presentation.
Thank you so much, Bhaskar, and also Craig and Brienne for your organization of this series. It's been fascinating. So let's jump right into things. In terms of the talk, hold on one second here. So I should underscore that I'm clearly not an expert in virology or epidemiology. However, as the pandemic unrolled, we realized that there were some interesting opportunities for someone with my group's skill set to get involved. And I should highlight that this is essentially the work of a wonderful PhD student in my group, Dhruva Karthik, as well as collaboration with Ashutosh Nair, another colleague in electrical and computer engineering. And we've begun discussions with Peter Kuhn in biological sciences and Yortsos in public policy to make our work more practical and take in specific issues that exist with these various tests. So let me start at the beginning. Essentially what we're interested in is this question of the design of experiments. If we are trying to figure out some kind of phenomenon, can we choose a series of experiments that will give us important observations that will help us assess what we're trying to determine? And many attribute this particular area of work to Sir Ronald Fisher, who some of us may be familiar with in the context of Fisher information and bounds on estimation. He was a very prolific statistician, although especially given our current time, he would be considered a very complicated individual because he was a big proponent of eugenics. So the individuals who I think are much more important to the work that we've been doing here are Chernoff, who is still with us, so you might recall Chernoff bounds for decision theory, Abraham Wald, and I'll talk about his work in a minute. And one of my favorites here is David Blackwell, who was a faculty member of statistics at Berkeley. He did not write a lot of papers, but for those of you who are in systems theory, I would highly encourage you to read them, because every paper he wrote was truly a gem. And his work had a profound impact on estimation, and especially in this area here, experiment design. So I think I can pride myself in having fewer equations than Yannis did, but I do have a few. So how does sequential probability ratio testing work? So let's say I have two hypotheses or two choices that might be true, and the statistics underlying my observations are a function of which one of those hypotheses is the real one. And so in SPRTs, what you do is you collect observations until you're confident. And so this likelihood ratio function is accumulated over a series of observations, and you can see a physical depiction of this here. And if the value of this is in between two thresholds, then you decide that you're not confident yet, and you take another observation. And of course, there's noise in the system and other variations. And so you design these thresholds A and B such that when your likelihood function of the accumulated likelihood function passes one of these thresholds, then you're truly confident that one of these is true. Now, for this example that I've shown here, we're essentially applying the same experiment over and over again, all right? So that experiment choice is not present here. I want to give you an example of how, or reasons for why you might want to vary the experiment. So this is an image from some work that we did in the past in collaboration with a large number of colleagues, both in ECE as well as computer science, where we were building wireless body area sensing networks. And so we were instrumenting individuals with sensors. And the goal was to try to figure out what physical state they were in. And so we modeled this very abstractly as being a Markov chain here. And so these numbers correspond to different physical states you could be in, like sitting or standing. And then we made estimates of the probability of you going from, say, a sitting state to a standing state, etc. Now, what we had at our disposal, and because of the fact that our wireless body area sensing network was really limited by the sensors we were using and the systems we were using, which was a mobile phone as our detection unit. And of course, mobile phones were not designed to be biometric signal processing devices. And so a challenge that we had was the phones could only listen to one sensor at a time. The other challenge that we had is that each sensor had different qualities in the sense that they were good at detecting some states and bad at detecting other states. But the goal was to design a strategy or a series of sensors to listen to, if you will, in order to determine which state we were in. And so if I can underscore this heterogeneity with this picture here, the challenge that we had was that each of the sensors had a different cost associated with them, but also a different fidelity. And furthermore, that fidelity was often state dependent. So depending on what the true state was, that would change how accurate our sensors were. An important point to also underscore here is that whatever is the true state clearly is going to influence what your best experiment or observation mode is. So this brings us to the question of how do we assess how good an observation is? So this picture is aiming to elucidate that to some extent. So imagine that we have three different controls. I'm going to call them U. And I have a series of hypotheses that could be true. And depending on the control, the likelihood function or probability density function of each of these different hypotheses is going to differ. Now for this first control, every hypothesis has the exact same probability density function, which means that this control or this experiment mode is not very useful. In my next control, we see that there are differences, but they all have the same mean, but they have different variances. Whereas in my third control, these probability density functions have a greater separation between them. So at least visually, we can see that there's a difference, which suggests that distinguishing between these four hypotheses given this control is going to be easier to do. So this brings us to the question of how do we figure out these differences or distances between distributions? And if you take EE565, information theory. This is a measure that you will learn about, the Kullback-Leibler distance or relative entropy. It's also a measure that's re-emerging in its importance because it shows up in cost functions that are used to drive the training of neural networks. And so we can compute a distance between two probability distributions. Now, this is not a real distance, which provides us both with opportunities as well as challenges because it doesn't satisfy a triangle inequality. It's not symmetric. So the distance between P and Q is not the same as the distance between Q and P, but it is something that we're going to come back to. So let's get closer to the problem that we want to solve here, which is how do we design testing strategies to determine who in our population is infected with COVID-19, all right? Now, what we want to design is what's called an active hypothesis testing regime. And what we'd like to be able to do is to figure out a sequence of policies and experiments. And we want this sequence of policies and experiments to actually be data-driven. And so in the beginning, if we don't know which hypothesis is true, we might look at all of the candidate hypotheses and try a variety of experiments to get a better sense of which hypothesis might be true. As we become more confident, we're going to focus on the experiments in this picture, U3 and U2, which are going to give us more information or be more informative about here, the two choices that we have narrowed ourselves down to. So this dichotomy of processes is something that we call exploration and exploitation, and how we design strategies in these two different cases are going to differ. I'm not going to get into too much of the details of that, but just recognize that exploration strategies are often different from exploitation strategies. The other point that I want to make here is my choosing U3 at this point in time is a function of all of the observations that I've made through U1, U2 previously, and they're informing what I'm going to do next, hence the use of this term active. So, all right, and again, which experiment I choose is going to be a function of what the true hypothesis is. So I want to go back to this picture that we showed before and underscore that how I design that sequence of U's is going to be a function of the true hypothesis. All right, so what's the problem that I want to solve here? I'm going to start with a very simple instantiation, recognizing that it's overly idealistic, but then make it more practical. I have a series of M people in the population, and let's assume only one of them is allowed to be infected. And so what I can do is I have some controller, say a medical professional, that's going to decide who I'm going to test at what point. And so what I'm trying to figure out is this X, which is my true system state. Which one of these M people is in fact infected, all right? And we can see as time goes on, I will pick different individuals to test, and that's going to be my control or my experiment. And as a function of who I test, I'm going to get a different observation. All right, so in the beginning, I may test the first individual, they're not sick. Then I test number 5, they're not sick. Number 2, they're not sick. But finally, I hit individual number 3, and they are in fact infected, and I correctly detect that they are infected, okay? So there are distributions, statistical descriptions that are going to govern these observations that we take with each of these individuals. And practically speaking, this is information that we're going to have to learn and understand in order to design these tests. So, but for the moment, I'm going to assume that I know the probability density function of the observation if someone is infected or if they're not. And so what I want to do ultimately is design this sequence of experiments and at some point also make an inference, all right? So as I said, I have very little or very few equations here, but the ones that I do have are quite dense. I just want to underscore that what's going to govern how well our schemes work is going to be this number D star, which is the outcome of doing a max-min or min-max optimization over all possible pairs of divergences. And that in the end, there are going to be these distributions, alpha star and beta star, that are going to be important to us. So I'll come back to that in a bit. But a technical point that I want to share is that one of Dhruva's great contributions in terms of this work is that most people looked at this active hypothesis testing problem and made statements about the asymptotic optimality of these series of experiments. And asymptotic means as the number of observations goes to infinity, which of course is completely impractical for us right now. What Dhruva has been able to come up with is very strong upper and lower bounds that govern or describe the performance of taking a finite number of observations. So there are a number of comparison cases I want to give you just to show you the strength of these theoretical results. One is an open loop randomized strategy, which says I pick a strategy or a percentage of the time of what tests I'm going to use. And I do this once. So I say I'm going to use test 1 20% of the time, test 3 50% of the time, and test 3 the other 30% of the time. And I use this strategy over and over again, and I flip some multi-faced coin at each experiment stage to decide what test I'm going to use. Our strategy is deterministic but adaptive. It takes the observations or the outcomes of each of the previous tests and decides what the next thing is to do. Okay, and so this is just to show you that these bounds are very tight, and in particular, this lower bound here gives us hope that the strategies that we've come up with are not just asymptotically optimal, but they're also finite horizon optimal. All right, so now let's focus on the problem at hand, which is what I described to you before in some ways is not very realistic, because I'm suggesting that you test each individual multiple times, but I test each individual by themselves, if you will. One of the things that we've seen is that there's a shortage of tests. So this proposition to test everybody multiple times does not make sense. So what we want to do, and this is not an idea unique to us, is to see if we can get samples from different kinds of locations and potentially test them simultaneously. So there are a couple of questions that we need to ask and answer, which is, what are the good testing strategies? And to also recognize that one of the things that's been revealed to us in the context, especially of the serological tests for antibodies, is that all of the tests out there are not built the same. All right, so some tests are more accurate than other tests. And so you might ask yourself, if I have these tests that are inaccurate, should we just not use them at all? Because the outcome of these tests don't give us high fidelity. And the answer to this that we're going to show is that, in fact, there is a role for cheap, inaccurate tests to play in the context of testing a population. And so what we want to do is an old idea, and that is pool tests. So this is something that was used actually in World War II to test soldiers for syphilis, where there were not enough syphilis tests present. This was a blood-based test. And so what they would do was take samples from large populations or larger populations of individuals, pool them together, and if one or more of the individuals in this pool were positive for the disease that was being tested for, they could then decide to look at that particular group. So here we've taken all of our soldiers, we've divided them into 2 groups. In this case, only one person is infected. We apply one test here and one test here. Only one of them turns out to be positive. So then we go back to this group, we further divide their samples into 2 different groups, et cetera, et cetera. And so you can see what we're doing here is essentially binary search, and we're creating a tree for testing all of the possible individuals. The important point, of course, is that we go from n tests for n individuals to something that's logarithmic in n, which is a much smaller number. Okay, and so what I would like to show you here is the use of this pooling idea with the tests that we've designed, testing strategies, the active testing that Dhruva has done in his PhD work. And now what turns out to be how we define our experiment is how we define the group. So you can imagine that one experiment is to test individuals 1 through 4. Another experiment is to test individuals 5 through 8. So this is a simple situation where we have only 5 people, if you will, that we're testing. And what you see at the beginning, so this is a case where only one individual is sick. So the beginning is at the bottom of the plot here. We test everybody, all right? And as we go forward, there is this sort of random collection of groups that we're creating. And as we do these group tests, we're getting more and more information about who is sick and who is not. And eventually, we focus on retesting the individual who is still sick, who's the only one who's sick here. If you look at the right-hand side of the slide, here's a scenario where, in fact, we have designed things under the assumption that at most one individual is sick, but in fact, nobody is sick. And so what happens there is you end up testing the entire group over and over again to confirm the fact that nobody in this population is sick. Now we can change things to have multiple anomalies. We can also change things to give each individual a different prior probability of being sick or not sick. And so a couple of numerical results that I want to share with you before I come to the end of things is that whether you have prior information about an individual being sick or not actually largely affects the number of tests that you have to conduct. So what we have here is a total number of tests versus the number of individuals. Now, a very important point for me to underscore here is that I'm assuming that I have two kinds of tests, one that is 80% accurate and one that is 90% accurate, all right? And so the accuracy of the test makes an impact and the prior information makes an impact. And so the key point here is that if I use these group testing strategies, exploiting this prior information, one of the things that I can do is increase the overall accuracy of the test. So one of the reasons why you see this individual testing skyrocketing is that I'm doing retesting in order to improve the accuracy of the overall system, all right? So I'm able to do retesting to improve my accuracy from 80% or 90% to 99.99%, right? Another thing we can do is introduce different kinds of testing strategies that have different qualities and combine them. And so this is also showing that you can achieve very high accuracy by doing smart group formation and doing retesting. And what you find, if you go back to those images that I showed you before, how the groups are formed is that you do cheap testing in the beginning, and then you focus on more expensive testing later. Okay, so there are a number of challenges to this strategy that I'm proposing, especially this active hypothesis testing and the work that we're doing right now. First is that it's computationally very expensive. And so a natural thing for people to consider right now is the use of machine learning and neural network techniques in order to compute the optimal solution. This is not as straightforward as it sounds. If you apply a black box strategy to testing, there are a number of things that the classical strategies are not well designed to do. And one of them is outputting what the optimal experiment choice is at each time instant. And so initially, for example, we tried using recursive neural networks, which we thought, okay, this seems to make a lot of sense. It's recursive in nature. We have a recursive problem. But it turned out to not work very well due to the complexity of finding the right objective functions for it to optimize. So a point that I want to say is that for problems like this, you have to design your neural network architectures very carefully. You have to use domain knowledge. And one of the pieces of knowledge that we used was structural properties about our optimal test, which was computationally expensive. And then when we did that, we were able to design strategies that worked well. So this is earlier work than the active testing work that I just showed you, where we were able to design a deep Q network, which came very close to finding the best policy. We found that a heuristic strategy that was data-driven and much easier to implement and didn't need any training actually worked very close in terms of performance with the strategy that's learned by the neural network. So we're getting towards the end. Let me just say a few short words about other strategies. Clearly, this idea of group testing and pooling samples is an obvious one, and we're not the only group that's working on that. I wanted to draw a contrast to the strategies that other people are using. So ours are data-driven and adaptive. Another strategy is to do pooling, but in a fixed and static way, all right? And so what you essentially do is come up with ways of combining all of the observations you have, and I'm putting this in a linear algebra context because that's literally what you do. And the challenges there are designing the pooling that you're going to do. This can be done in a randomized fashion. People are using coding theory, so ideas from low-density parity check codes, as well as other strategies, even those that are based on the classical binary search strategy. And then these are fed into some kind of optimization box. And so people are using things like compressed sensing, generalized approximate message passing, et cetera, as well as decoders that we use in coding theory. So these are not adaptive strategies, but they can be parallelized. And so there are some benefits to using schemes like this. So again, our method is data adaptive, all right, but it's more challenging to make parallel. The kind of test that you use is actually going to matter. So it's easy to pool blood tests, but that's not how these blood tests are being applied right now. Right now you do a finger prick, it goes into a machine, it can be done while you're standing there. So how do we come up with mechanisms to pool these samples in a smart way? We've heard about the gold standard for testing for the presence of the virus in each of us. These are these PCR tests, but you've also probably heard that these tests are uncomfortable because essentially a swab is shoved up your nostril. You know, so we could do this many times, but then how do we intelligently pool all of those swabs together, all right? So I want to note that it appears that pooling is something that Wuhan did in order to quickly test its population and cover everybody. But you know, there are still challenges here. And so now one of the things that's come up is that as great as these PCR tests are, if you test at the wrong time, you may not get accurate results. And so this issue of time zero, moment of infection, is something that we need to work into the work that we're doing, the research that we're doing, to understand the best way of testing people. But of course, we want to find people before they become symptomatic, because as asymptomatic carriers, there's the potential for infecting others. So let me end things here by saying that our focus has been looking at how do we come up with optimized solutions for active adaptive testing with a finite number of observations. There are very nice technical results that we can state about our work, but we believe it also has practical implications. One of the nice things about our work is that we can accommodate all different kinds of prior information, and we can come up with strategies for combining tests of differing accuracies. We also believe that we can expand the applications of this work by looking at how we can come up with active testing strategies for figuring out hotspots geospatially. And so I will end things there. Thank you.
Thank you so much. So let's ask our audience members to post their questions on the Q&A. And perhaps while that's coming up, I just have a quick question about kind of the trade-off between false positives and false negatives and how they might affect the strategies that you're describing.
So, Bhaskar, you raise a very good point. What I will say is false positive rates and false negative rates are part of the experiment design. However, one of the things that we have not done is understand the relative influences of each of these. The other thing that's important to note is for all of the numerical results that you saw, we had a target accuracy with respect to false positive and false negative that we were trying to hit, all right? And so the idea is that you keep doing tests until you achieve the accuracy that you want, all right? But it can be done the other way. I can only make so many tests, and at some point I have to stop, and therefore at that point I can tell you the accuracies that you're going to achieve. Right? So this is all built into what you're doing, right? And this is also where these bounds are very useful, because you don't have to go through all of the tests to actually determine, you know, the rates that you can expect. So even though it's a very theoretical result, we believe these bounds will be very useful for actually doing testing regime design.
Great. And have you been talking to some of the folks at USC that are involved with these, with the testing studies and so on?
Absolutely. And so I should have emphasized that more at the beginning, but so as I said, Peter Kuhn, who has so many affiliations, they're too long to list, biology, medicine, BME, AME, he has been keeping us a little bit honest in terms of what we can expect on the pooling side, because as I said, it's easy for us to say, let's just pool the samples, but there are practical implications and challenges with pooling samples for different kinds of tests. And then Professor Neeraj Sood, who's in public policy, who's been doing these serological tests across LA County, has been extremely generous, and he's about to share his data sets with us. And so this last slide actually relates to that, because one of the things that we'd like to be able to do is analyze the existing data he's taken to get an understanding for what some of these probabilities are, and then potentially come up with testing strategies for his people for the future tests that they do. And the interesting prior information here, which will allow us to maybe do things in an active way, is that, the 1,000 of people that he tested he's done 2 rounds, as I understand it, they were not all tested on one day, right? And so we might be able to suggest how to test in different geographical regions a priori. As information is collected, we can use that to say, who should you test next, again, geospatially. And if you're trying to understand where hotspots are versus just trying to identify infected individuals, you still have to do some exploration of regions where you think there is a low density of COVID-19, all right? And so testing to figure out who is sick is a different strategy than testing to figure out where hotspots are in LA County, all right? And so these are some of the differences we expect to see as we analyze some of his data. But, again, the question that you ask very much defines the strategy that you should use.
Great. I think we're not seeing other questions from the Q&A, so we'll thank you for your presentation. And
thank you so much.
Thanks to all of you for joining us. Bye.
Bye-bye.